Networking sounds like a giant pile of acronyms from IP to DHCP, NAT, BGP, TLS, and the rest. Here's the trick when you are trying to study networking. All these things that you see forms part of a chain. So each idea exists purposely to solve the exact problem the one before it left behind. So for example, if two devices need to communicate, they need a link. And in this case, the link is mostly something we reference as Ethernet. And then this link needs an identity. So that gives us addresses. And it's built step by step from a very single cable all the way up to load balancers, which is pretty much running all the biggest web applications and websites on the planet. So when you follow the chain, you understand all these components, and then all these acronyms that you see in networking would make sense. Let's start from the very bottom. Everything starts with a physical connection. When two devices want to communicate, right, these two devices literally cannot exchange a single byte or bit of data or information until there is something carrying it between them. That is Ethernet. So the Ethernet is just moving the data over a physical cable or your Wi-Fi that you use, and then which is pretty much doing the same thing or transferring the same data, just that in this case, our Wi-Fi transfer the data over air instead. So now I want you to picture this as a road. You see, we haven't talked about addresses or traffic rules yet, but just understand it this way. At this point, what we've done is that we've laid down the pavement and everything else travels on that pavement. So now we've got our road. So how then does data, which is pretty much our files, our videos, our web pages, travels down it? You see, it does not travel as one big lump of data, but rather what happens is that it is chopped into smaller chunks, and then in networking we reference that as packets. So each packet is sent separately, and then in fact they can take a different route. But what happens is that they are reassembled in order at the recipient's end. Why do we bother converting our data into packets? You see, the thing is that during transmission or during sending of data, there is a possibility of some going missing. And then if we break down it into smaller pieces, what happens is that if any of the packets or if any of the chunks gets missing, you don't have to resend the entire thing, but rather you just go ahead and then send just the missing piece. So instead of you losing your entire data just because a single chunk got dropped, what happens is that it is easy for you to resend just that chunk or just that packet instead of sending the entire thing. Imagine having your file destroyed just because a packet got dropped. So now, up until this point, you've got our wire, and then we understand how things transfer through our wire, that is through packets. But then there is a question: who are these packets for? If two devices are connected, they still need a way to tell each other apart. So every network card or any network component that you see has a unique hardware ID built into it at its factory. This is called a MAC address. MAC stands for Media Access Control. Your device MAC address never changes. It is how devices recognize each other on a local link. The key word I want you to know here is this: a local link. A MAC address works between machines that share a connection, and in the next few minutes you are going to understand that this isn't enough for us to reach the wider world. So when you are trying to connect two devices, that is pretty easy, right? You just need one cable and then you're good to go. But what about you trying to connect to 10 devices, 100, or even say thousands or millions of devices? You can't run cable from each of the machines connecting all of them, right? So to help us deal with this, this is what a switch is needed for. Everything is plugged into a switch, and then when packets come in, it reads the destination MAC address and then it sends the packet only to that device that said packet or that said data is meant to go. Now, looking at the picture on the left, you realize that we have another older device called a hub. A hub is pretty much a dump version of the switch. It copies every packet to every port. So with hub, what happens is that once the data comes to the hub, instead of it sending it to a specific destination, it broadcasts it across all its openings, which we mostly reference as ports. It broadcasts it across all its ports, and everyone on the network receives that data. So with switch, it's pretty much one packet and then its specific destinations. But with hub, one packet and everyone receives it. Now let's come back to this limitation of a MAC address. A MAC address only works locally. That is, it exchanges data between machines on the same link. So to reach a device on a different network or a device across town or other parts of the world, you need an address that works pretty much everywhere. And that brings us to IP addresses. That's Internet Protocol. Unlike the MAC address, the IP address is not burnt into the hardware. The IP address is logical. It can change and it is structured so that the network can figure out where it lives. So see it this way. If the MAC address is the name on your office door, the IP address is your full mailing address. So now, where does this IP addresses come from? There are two ways through which we can get our IP address. You can set it by hand, which we mostly reference as a static IP. So for example, you have something like a server and then you don't want the address to change, you need the same address. What you do is you can manually key in your IP address and then that would work. But a far more common approach is to handle this using something we call DHCP, which is Dynamic Host Configuration Protocol. DHCP automatically handles assigning of this IP address to your devices. So the moment you join a network, DHCP hands your device a free address. So you don't have to type or you don't have to assign any IP address to your devices. This is the main reason why your Wi-Fi works when you get connected to it. So pretty much static IP is you picking your own seats and DHCP is you waiting for your host to show you exactly which of the seats is for you. Now here's a question hiding inside every IP address you see. You see, which part of the IP address tells what network you are on? Which part of the IP address identifies you on the network? That split, which talks about which part is the network and which part identifies you, is something we reference as a subnet mask. You've seen it written mostly as a /24. That pretty much means that the first chunk of the address is the network and then the rest is the host. So this is pretty much how network devices knows that this address is one of my neighbors I can talk to directly versus this device is far away and then I need it to send it out to the wider world. So up until this point, I keep on referencing two worlds, right? Whether our local world or the wider world. The first I'm going to talk about is LAN, which stands for Local Area Network. This could be your home network or your office. Pretty much, this talks about all the devices that forms part of that switch we talked about earlier, right? And then we have a WAN, which means a wide area network. A WAN pretty much spans huge distances, linking networks across cities, continents, and the rest. And in fact, the biggest one of all is the one that pretty much connects all of us together, which is the internet. So now I want you to understand this way. You see the LAN to be your own street, right? Where you manage stuff to send things between your devices and all that. And then the WAN to be all other routes that links all parts of the world together. Now the question is that how then you move things from your own street, that is from your land, up onto these wider networks in the world or wider road networks in the world? The thing that actually does it is the router. So we've come to understand that a switch moves data within your own local network. What a router does is that it moves data between networks. So it reads each packet's destination IP, looks at where that address lives, and then it forwards that packet one step closer. So see your router to be that it's at the edge of your network, and then it looks at whatever you want to transfer, and then it determines how to push it into these wider routes or other connections that you have established. So every packet leaving your home address passes through your router. So now, how does your router know how to hand the packets to the router in the first place? So now there is a simple rule. If the destination of the packet or the data you are trying to transfer isn't a local neighbor, remember, we're able to determine the destination by looking at the subject mask, right? So if this destination isn't on your local neighbor, then what you do is that you send it to your default gateway. And then your default gateway in most networks is almost always your router. And then that figures things out from that point onwards. So your router is pretty much the catch-all exits on your network. So the fact is that your device doesn't need to understand the whole internet. It just needs to know one address to forward anything it can't handle directly to. So it's pretty much, oh, I don't know how to handle this data, or I don't know how to handle these packets. And then it dumps it to your default gateway, which is pretty much your router, and then it takes it up from there. So now we've understood that everything leaving your networks heads through your router, right? But there is one key catch on the way out. The IP your laptop has at home is a private IP. It only means something inside your local area network, that's inside your LAN. There aren't enough public addresses in the world for every device to have its own. The way of fixing this is something referenced as NAT, network address translation. So what happens is this: your router takes all your private devices and make them share one public address to the outside world. And once it does that, it keeps track of who asked for what, so that when replies come back, it knows the right device or the right path to take it. So it sees this way that there's more like one office phone number with many internal extensions, right? So the whole world calls into one number. Once it gets to that number, there is a reception which kind of routes the call to the appropriate office or the appropriate quarters. So now we've understood that our router forwards packets, right? But how does it decide where each one or each packet goes? It follows something we reference as routes. A route is just a rule. So it pretty much says that for a traffic going to this destination, send it out this way. A router keeps a whole table of them. And then the default gateway we just met is simply the catch-all route. So what that means is that anything I don't have a specific rule for, send them through the default gateway. When you manually type in your route, we reference that as static routing. This is perfectly fine for small, stable setup, right? So it's more like you having a few signposts you put up once and then that is it, and everything works fine. But what happens if you've got hundreds of networks to manage? Once you've got hundreds of networks to manage, typing routes by hand is pretty much hopeless and then it's not possible. This is why. You see, if one of the links goes down, every signpost suddenly is wrong because the directions are not going to work fine. So inside big organizations and big networks, what happens is that routers talk to each other. This gives us something referenced as OSPF. That is Open Shortest Path First. So this is pretty much a protocol where the routers on your network, right, share what they can see automatically. And then this results in them automatically working out the best path for everything that you send on the network. And then the benefits of this is that this gives them the room to reroute if any of the links that you are trying to establish fails. So I want you to picture this. Think of all the routers in a company constantly comparing nodes so that traffic always takes the smartest route with no human updating any tables or doing any configurations. There is another catch here. OSPF kind of handles this perfectly fine within one organization. But here's the case: the internet that we are all working on is not just one organization. So the internet, as you know, is tens of thousands of separate networks in different companies from different countries and different continents. And the key thing is that none of these companies and networks take orders from each other. But here's the case: they need a way to exchange directions across those boundaries that are between us, right? This is where BGP comes in. BGP is Border Gateway Protocol. So with BGP, each network announces, here is how to reach the addresses I'm responsible for. So what happens is that BGP stitches all those announcements into a global map that lets any packets find any destination on the planet Earth we're dealing with, right? So BGP is genuinely the protocol that holds the entire internet together. Up until this point, we've built our own network from our local network up until the whole world. Let's actually test it. You see, ping is the simplest tool in networking. What it does is this: it finds a tiny packet at a host and then it proceeds to times how long it takes to get a reply. So if you get a reply, then what that means is that the device you are trying to reach is reachable or is available. If you don't get a reply or a response, then that means that something is broken along the chain or along the line. So this is the most common thing that a lot of network engineers do. When they are not able to access a website, the first thing they do is they try to ping the address to ensure that that address is accessible. If they don't get a response, then it means it's not accessible. The thing is that when you ping a network or when you ping an address, it tells you if you're able to reach it or not. But with trace routes, right? Trace route tells you the whole journey. So what it does is that trace route reveals every router, every hub your packet passed through up until it goes to its destination. And then also it tells you the time it took at each one of them. This is everything we just learned being made visible. When a connection is low or dead, trace route shows you exactly which hop had a problem. So it's pretty much more like a live map of the road your data actually takes the moment you transfer it. So now let's talk about bandwidth and latency. Bandwidth is how much data fish through at once. So for example, you have a pipe. When we talk of a bandwidth, we are saying how much data fish through the rate of this pipe at once. Whereby latency is how long does it take for each bit to arrive. So with latency, we are looking at the delay. The thing is that you can have a huge bandwidth and then still things will feel slow if the latency is high. This is why a video call from the other side of the planet lags even if you're on a faster fiber or on a faster network. The thing is that when you have a wider pipe, right, it doesn't necessarily mean that water is going to travel any faster. What it just does for you is that it's going to allow a lot of water to travel at that time. Now let's talk about TCP and UDP. You see, remember we talked about packets getting lost or packets arriving out of order. How much you care about that determines which of the two methods to use. TCP, which stands for Transmission Control Protocol, sets up a proper communication. It numbers every packet and then it resends everything that gets missing or goes missing along the way. So with TCP, you are sure that your data always arrive complete and in order. TCP in itself is safe but slower. Now with UDP, which stands for User Datagram Protocol, UDP just fires packets off and doesn't look back. So there is no setup and there is no resending mechanism. UDP is faster. So a clear use case of these two protocols is this. If you want to download a file from the internet or somewhere to your local, what you mostly use is use TCP. This is because if you lose any of your bits and then it's not resend, it's going to affect the integrity of your file. But for example, if you're on a video call and then you're having a call with someone, what you do is you prefer to have that over a UDP. This is because during your live calls, if a video frame drops, what you don't want is to be waiting for it to be resent, else that is going to even make the whole call experience work. So once a video, a bit or a packet or a chunk or something gets dropped, you just proceed. You don't really worry so much about it. So that's a clear use case of both of these protocols. Now let's talk about ports. We've gotten to understand that with the help of our IP addresses, we're able to get our data to the right devices. But our devices, whether our laptops or whatever device you're using, runs a lot of applications, right? From running our browsers to our email client to different other things. So now, once the device receives this packet or this data, how then does it determine where this packet goes? We are able to do that through something referenced as a port number. Every connection carries a port that says which application that data is for. There are some common ones which are pretty famous that we hear often or you're going to hear often. Example is 4434 for secure web connections. We have port 22 for remote logins. We have port 53 for DNS stuff and a whole range of them. So the full picture is this. The IP address helps you to kind of find the building, right? But the port number helps you to find the specific door inside that building. So together, they're able to help you deliver your data, not just to your laptop or your device, but it also allows them to send you to the exact application waiting for that data. Now let's talk about a firewall. You see, up until this point, data is freely moving in and out of your network. But the thing is that you don't need probably all of it. You don't want every data or anything being able to come in and out of your network freely. That is where a firewall comes in. So a firewall is pretty much a gatekeeper. So it pretty much inspects traffic and decides what is allowed. So it also can be used in blocking specific ports, specific addresses, and then any kind of connections that you don't want. So maybe you allow web traffic on port 443, but block everything else trying to reach your network from any other ports. So your firewall is pretty much a guard at your door checking everyone against a list of rules that you kind of defined, right? So what that you are saying is that, oh, let the good ones come in and then turn the bad ones away. So the firewall is where we cross from making our networks just work into making them safe and secure. Now let's talk about TLS and SSL. You see, here's an uncomfortable truth. You see, packets pass through different routers and different networks that you don't control. And by default, anyone in the middle can access your data and then read them. Especially on a public Wi-Fi, right? Anyone nearby can intercept your data and then read them. This is where TLS comes in. TLS stands for Transport Layer Security. You see, what this does is that it fixes this problem by encrypting the connection. So what happens is that even if someone intercepts your packet, all they see is scrambled nonsense, right? So they are not able to make sense of whatever you are transferring. It is only the two endpoints that can read the data you are transferring. That is the sender and then the actual recipient. You often hear SSL. SSL, which stands for Secure Socket Layer, is just an older name for TLS. So it's pretty much the same idea. Now, what is a VPN? So we've understood or we've just learned what a TLS is. But the thing is that TLS protects one connection at a time. So it protects, just say, one site at a time. But what if you want to protect virtually everything? Or you want to reach into a private network from the outside? That is where a VPN comes in, a virtual private network. So what a VPN does is this. It builds one encrypted tunnel between you and another network. And then once it does that, it shows all your traffic through it. So to anyone watching your network, what they will see is that they can't see the site you visit or what is inside. All that they see is just one seal pipe that is kind of transferring virtually everything. This is how remote workers safely reach their office network. This is how a lot of people shield their browsing, especially when they are browsing on untrusted Wi-Fi or on public internet. So the difference is this. TLS kind of seals everything in one envelope, where a VPN kind of runs a private pipe for you through the public space or the public internet. Now let's talk about DNS, domain name system. This whole time we've been talking about reaching networks through something referenced as IP addresses. But honestly, when you are trying to access any website or any site, what you do is that you type the site.com, say site.com, or you type the site name.com or something. Because we are typing, say, a name or word that makes sense to human, then we need something that will kind of resolve or convert it into the actual IP address behind it. That is where a DNS comes in. Every time you type your website or every time you load your website, your device quietly asks DNS, what is the actual IP address for this name that we are trying to access? And then it gets the IP address number back, and then that's when all the things that we've talked about happens, and then we're able to send our data and our packets through to that network. Now that you know how DNS works, now there is something we can use to monitor exactly what happens by doing NSLookup. This is actually something your device or your laptop does silently 1,000 times a day. NSLookup, which simply stands for name server lookup. So anytime you type in the name, what NSLookup allows you to do is that it it asks DNS directly, what IP address does this name points to? So you can run NSLookup on any site, and then you see how it resolves it and then gives you the necessary details. So once you run it, it tells you the server information, the name, and then the actual address you are looking at. So now let's talk about HTTP, Hypertext Transfer Protocol. So this is pretty much a very simple, beautiful conversation. So what happens is that your browser pretty much says this, get me this page, and then a server replies back to it, here's the page, and then it gives it, say, a 200 OK response. This back and forth we just talked about pretty much happens every single time, every time you try to access a page, load an image, or do anything on the web. So it's very simple. If you want to access something on the internet, all we are doing is that we are sending in a request, and then we are getting back a response or a reply. So I need this, and then it gives you a response. Okay, this is possible. Or no, this is not readily possible for you to have. Now let's talk about HTTPS. So this is pretty much two pieces that we've talked about. So now we've talked about HTTP being us sending a request and getting back a reply or a response. But the moment we wrap it with a TLS, that is, the moment we add encryption to this, then it becomes HTTPS, which is Hypertext Transfer Protocol Secure. So it's the same thing, just that at this point, we are not allowing people to have access to it or to be able to read or tamper with it. We are making and ensuring that the same conversation we are talking about, that is our request and reply conversation, is secure. So the best way you can see is that anytime you are accessing a browser, you realize that there is a small padlock icon in your browser, And then that tells you that, oh, indeed, this site or this page I'm trying to access, it's actually secured or not. Now, the last thing we are going to talk about is a load balancer. So up until this point, we've talked about how we're able to communicate, sending requests, getting response, and doing all that. The thing is that if there is a site that you are trying to access, for say there is a popular website that you are trying to access, the site doesn't just give you just you response. So this gives us the need for site to scale. This is where a load balancer comes in. So you might have a lot of identical servers behind the scenes. What you do is that you put a device in front of it. That's we reference as a load balancer. And what this load balancer does is that it takes in all the incoming traffic and then, or the incoming request, and then it sends it to all the available servers, right? So if a server dies, your load balancer then stops sending traffic to that particular server. The OSI and its TCP IP models. So I want us to step all the way back and look at what we've built from the very beginning. Everything we've built stacks on top of each other. At the bottom right, we started by having a physical cable or Wi-Fi. And above that, we talked about being able to communicate using our MAC addresses and switches. Then we came to IP and route. Then we talked about TCP and UDP. Then we spoke about the importance of having ports, which tells exactly where that goes. And then finally, how our apps works on the web, right, through HTTP and HTTPS. Now, all these things can be broken down into two major stacks. The famous one is the OSI model. That is the Open Systems Interconnection model. This involves 7 layers that stacks up from all the things that we've spoken about from the very beginning. This is pretty much the most common thing you will see in almost every textbook when it comes to networking. But the internet currently now runs on a very simpler model that is a 4-layer map, right? Which is the TCP and IP model. The difference is that the TCP IP model kind of bundles the 7 layers into 4 layers. So with the TCP, you have a link, internet, transport, and application. Under the hood, it's pretty much the same things happening, just that we are bundling a couple of them. The thing is, you don't need to memorize this list. But what you need to do is to understand the path data takes as it travels over networks, as it moves from your end up until it gets to the recipient's network. And the best way of doing that is capturing it using the OSI model we spoke about. And this is pretty much networking end to end. Thank you so much for watching. If you liked this video, kindly give us a like, subscribe, drop a comment, and then let's meet in the next video.